Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will implement logistic regression from scratch. Okay, so let's get started. So first we would require one library to import, which is NumPy. Let's import NumPy as the NP, right? And let's define class logistic regression, right? So in previous video, we understand how gradient descent work and how we can train any machine learning model. And in logistic regression video, we understand how logistic regression works with geometric and mathematical intuition, right? So if you haven't seen that video, please go to my playlist and check out this video. Okay. So let's first define few methods which we will implement after. Let's say first constructor or init method. I'm writing currently pass. We will implement it after defining all methods, right? So then we would require one method which is sigmoid, right? We are using sigmoid function in logistic regression. Let's define a loss function, right? So we can check how loss is decreasing over the each iteration. Pass. Let's define fit method. So fit method basically contain all the code related to training. Okay. And last, define predict. Okay. So let's start from this init method. So while the logistic regression object will generated, we'll assign some variable. Let's say first is learning rate. So default learning rate would be, let's say 0.01, and the second argument would be number of iterations, right? Let's say 1000. Okay. Let's assign into the class variable self.learning_rate is equal to learning rate self.number of iteration is equal to number of iterations. Okay. Let's define weight and biases as well. So at initial level, we are just putting none value in that. Self.bias also none. Okay. So these are the four parameter we initialized, right? So now let's see what is the sigmoid function. So if you recall the previous videos, sigmoid function is basically sigmoid of x is equal to 1 upon 1 plus e raised to minus x, right? Let me write x. Right? So let's implement it here. So we can write return 1 divided by 1 plus, in NumPy we had one exp function which do this e raised to thing, right? So e raised to minus, let's say z, from where we will receive z. So z would be our argument here, right? So this is all about sigmoid function. Now let's define the loss function here. So here we will use log loss for the loss function, right? So if you recall a previous video, the loss function is, let me write it here, loss is equal to negative 1 by n sigma I is equal to 1 to n yi into log pi plus 1 minus yi into log 1 minus pi, right? Where pi is probability of given point, let's say xi. Okay, so which can be derived as sigmoid of w transpose xi plus b, right? So let's define this loss function in our function in the loss here. So let me write here. Yeah. So let's say loss is equal to this negative sign and p dot mean, right? So basically, when we are dividing, here we are doing 1 upon n, right? 1 divided by n. So we are basically taking the average of this whole term, right? So let's say mean, and we would require p and y here. Okay, so y is actual label and p is a probability which we will predict. Okay, so let me write here like y star np dot log p. Okay, this term y into log p, then plus y 1 minus y multiply with np dot log 1 minus p, right? So we had written this loss function in the numpy formula. Okay, so now let's move, let me return this loss function first, return loss. Okay, so now let's move towards the training code, right? So for fit method which will do the training, we would require x train and y train, right? So let's implement this fit method. So first of all, we would require how many features are there, right? Based on that, we will initialize our weight vector. So let's say number of samples and number of features is equal to xtrain.shape, right? So it will return number of rows and number of columns. So number of columns is our features, right? So let's define weights is equal to np.zeros number of features, right? So we are initializing our weights with 0 value, right? Then we will train them. Let's define bias as well. So bias is one scalar value, so we will just put 0 there, right? Okay, there is some spelling mistake for the features, let me correct it. Okay, so now we have our bias and weights which are initialized with the 0, right? Okay, so now we will perform gradient descent operation, right? So in gradient descent, it is the iterative algorithm, right? So we had defined the number of iteration here. For that much iteration, it will perform weight updation, right? So let's write first for iteration in a range of self dot number of iterations, right? Now here we have to update a weight. So what is the formula of updating a weight using gradient descent? So it is, we had seen that, right? So w new is equal to w old minus eta times derivative of loss with respect to w, right? Right? So let's implement it here. First let's predict the value, right? So for calculating the loss we need prediction, right? So what will be the prediction? Prediction is equal to self.sigmoid, because we are doing this like sigmoid of w transpose xib, so we are just writing that. Okay, so let's say x train np dot, right? We have to multiply them, np dot x train with self dot weights, right? And we need to add bias, self dot bias, right? So this would be our prediction. Okay, so now we need to update our weight. So before updating weight, we would require this term, right? Derivative of differentiation of loss function with respect to w and with respect to bias. So we are using two variables w and b which we want to find, right? So if you derive, let me write it here. If you differentiate this loss function with respect to w, you will find this 1 by n, let me write it here, dl by dw, 1 by n sigma I is equal to 1 to n xi into probability minus yi. Okay, and if you differentiate it with respect to bias, you will receive 1 by n sigma I is equal to 1 p minus yi, whether p is a probability of given class, right? So let's implement this dl and dw here. So I am just keeping derivation of step by step here. If you want, I will create a new video in which we will learn how this loss function is differentiated with respect to w and bias. So if you want that video, please write it down in comment section. I will create a new video. Okay, so now let's implement this. So let's say dw, right? Dw basically dl by dw, right? So it can be written as 1 divided by number of samples, right? Okay, let me go here. Yeah, okay. I think there is some issue with it. Okay. Okay, so just remember this formula. We are just writing it here. Okay. Into np dot x trend dot transpose. What is here? Prediction minus y trend, right? Let me complete this bracket. So this will be our dw. For differentiation of loss function with respect to bias, it would be 1 divided by number of samples into, we need summation, right? So np dot sum prediction minus y trend, right? So now let's now let's update the weight and bias, right? So self dot weights is equal to self dot weights minus self dot learning rate into dw, right? So w new is equal to w old minus eta times derivative or differentiation of loss function with respect to w, right? So same thing we will write for bias term. Self dot bias is equal to self dot bias minus self dot learning rate into dB, right? So now our weight and bias updated according to gradient descent, right? So we are iterating for 1000 times, right? So let's print loss function how it is decreasing for each 25 steps, right? So let me write if iteration modulo 25 is equal to 0, then what we have to do, we will just calculate the loss function and print that loss, right? So for calculating loss we would require prediction, right? And now loss is equal to self dot loss function. It will require probability and our y, right? So let's say prediction and y trend. Okay, let me print it down. I will use f string here. So loss after iteration number iterations is here. Okay, and once after this for loop end or whole training process ends, we will again print the loss, okay, at the last time, right? So this is all about the training. So let's let me erase this here. Okay, so let's implement a predict method. So predict will require only x, right? And we had already written the prediction code here, so let's just copy it here. Instead of x trend we would require x, right? Weight and biases are already updated. Okay, so this is probability of positive class, right? But we want actual class value, right? So let's say predicted classes is equal to 1 if I greater than 0.5, else 0. And what is I? So let's say for I in prediction. Okay, and let's return this predicted classes. Okay, so this is all about the logistic regression. So let's run this code and fit and train on some data set. Okay, so for data set we will use sklearn library and dataset module. So let's say from sklearn dot datasets import make classification. Okay, so let import trend test split as well from sklearn dot model selection import trend test split, right? Let's import some metrics as well. sklearn dot matrix import accuracy score and confusion matrix, right? Okay, so let's import these three functions. Okay, invalid syntax, it's okay, so here there is a slash. Let's rerun. Yeah, okay, so let's create a data set, make classification, and samples would be 1000, right? Okay, and then and features, let's say I would require 15 features. Okay, so number of classes are already 2 there, so we are not defining again it. Okay, and let's define random state so we all can get same result. Random state, let's say 42. Okay, and let's split it into trend test, right? X train, X test, Y train, and Y test is equal to trend test split XY test size is equal to 0.2. So 20% data will be split into testing and 80% data will be in training side. Let's provide random state as well. Let's say 42 it again. Okay, so yes, we now have data set. Let's print the shape. Xtrain dot shape, ytrain dot shape. Let's put it this way so we get some, just understand how much data is there, right? So in training we have 800 samples, in testing we have 200 samples, right? So let's logistic regression, right? Let's do lr.fit xtrain and ytrain. Okay, okay, so it's my mistake, variable name. Okay, so let's, here as well it will be capital X, right? Okay, so let's train our logistic regression. So you can see at the 0 iteration we have loss at 0.69, right? And we are decreasing it at 1000 iteration we reached at 0.49, right? So loss is decreased as we train using gradient descent, right? So let's use this matrix to check out our result. Okay, so let's say y train prediction is equal to lr.predict x train. Okay, for same, let's say for test data set, okay, so now let's print accuracy. accuracy score, in which why it is not giving suggestion. Okay, yeah, so first we need to y train, which is for true label, and then y train pred, right? So let me write in the print statement accuracy, train accuracy, right? Same, let's say test accuracy we need to check. So we'll write here y test and y test pred, right? Let's print it out. So here we can see for training we receive 85% accuracy, and for testing we receive 88% accuracy. Okay. So let's check confusion matrix as well here, right? So let's say confusion matrix y train and y train pred, right? So this is training confusion matrix. Let's print test confusion matrix, right? Test. Okay. So this is confusion matrix. We can see there are a very less number which are falsely classified, right? As we know, we are getting 85 to 88% accuracy, right? Okay. So this is all about the custom implementation of logistic regression, right? So let's see the sklearn implementation for this logistic regression, right? So let me write here. Okay. scikit-learn SGD classifier, right? So in scikit-learn, let me open that page, right? Let's say scikit-learn SGD classifier. Okay, so if you go here, so basically this is the stochastic gradient descent classifier, and we have to pass loss functions here. So based on loss function, it will behave like logistic regression or SVM classifier, right? So if you provide loss function is equal to hinge, it will train a SVM, right, support vector machine, and if you provide loss is equal to log loss, then it will be your logistic regression, right? So this is stochastic gradient descent implementation, but we had implemented gradient descent, but we know the result would not that much differ, right? So let's see this implementation of the sklearn. Okay, so I will go here and let's just copy this code, right? Let paste it here. So we will not use this XY, right? We don't need this as well. Okay. Okay. So max iter is 1000. We also had used the number of iteration 1000, right? So let's say loss. We need to change the loss. By default, it is hinge, so it will train support vector machine. But we want logistic regression, right? So let's use log loss here, and instead of this, we will provide our data set X train and Y train, right? So let's train this. Okay, so it's a Y train is defined. Okay, yes. So Y should be smaller. Okay. Okay, so now we had trained stochastic gradient descent classifier with loss value log loss, which is basically logistic regression loss, right? Okay, so now let's do this prediction and check the accuracy, right? So I will reuse this code. Here I will pass CLF, right, which is basically for classifier. Let's see CLF. Okay, and we print this. Let's print. I'm just copy pasting the code because we had written already, right? Okay, so if you see here, in training we receive 0.82, that means 82% accuracy, and for testing we receive 84% 0.5% accuracy. In our implementation, we receive higher accuracy than this HDD classifier, right? But yes, we can improve this by tuning some parameter, right? But we can say we had implemented very good version of logistic regression as compared to scikit-learn, right? Okay, so this is all about the logistic regression implementation. If you have any queries, just write it down in comment section. We will discuss there. And if you like this video, please subscribe my channel and share it with your friends so they also can learn this thing, right? Thank you.